Jet engine power is restricted by the melting point of turbine blades. Afterburners bypass this bottleneck by injecting fuel into the exhaust stream after the turbine stage has already passed. Primary combustion consumes only about 1/4 of the available oxygen. The remaining 3/4 exit the turbine unused, providing a ready oxidant for secondary combustion in the afterburner duct. Thrust is the product of mass flow rate and the change in gas velocity. By heating the exhaust, we increase its volume and velocity, directly scaling the total momentum output.
An afterburner consists of fuel spray bars, flame holders, and a variable area nozzle. These components transform the tailpipe from a simple exhaust duct into a secondary high-energy combustion chamber. Exhaust gases move at hundreds of meters per second, far exceeding the speed of a flame front. Flame holders create low-velocity wake regions that allow the fire to remain anchored. Spray bars inject kerosene at high pressure to ensure rapid atomization. In the hot exhaust environment, these droplets vaporize almost instantly, preparing the mixture for spontaneous or piloted ignition. Adding heat at constant pressure causes the gas to expand. In the confined space of the engine, this expansion can only happen rearward, forcing the gas particles to accelerate significantly. As gas heats and expands, it requires more volume. Without increasing the nozzle exit area, the back pressure would rise and cause the engine compressor to stall or surge. At the nozzle throat, the gas reaches Mach 1. This condition, known as choked flow, means the mass flow rate is maximized for the given upstream pressure and temperature. To achieve supersonic exhaust, the nozzle must diverge after the throat. This allows the high-pressure gas to expand further, converting internal pressure energy into extreme kinetic velocity. In full afterburner, the engine approaches the stoichiometric limit, where every oxygen molecule is reacted. This produces the maximum possible temperature increase and the highest possible thrust boost. Afterburners are highly inefficient. While they can double thrust, fuel consumption can increase by a factor of 5 or more, making them suitable only for short bursts of speed. Total thrust also includes the pressure difference between the nozzle exit and the ambient atmosphere. If the exhaust is not fully expanded, this pressure thrust provides additional forward force. Shock diamonds appear when supersonic exhaust is over or underexpanded relative to ambient pressure. These standing waves are the result of the plume constantly adjusting to the atmosphere. The brightest part of a shock diamond is the Mach disk. This is a transverse shock wave where the flow abruptly slows from supersonic to subsonic, causing a massive temperature spike. High-energy combustion can trigger acoustic resonances, known as screech. If left unchecked, these pressure oscillations can vibrate the afterburner duct until the metal suffers fatigue failure. To prevent the outer duct from melting, a cooling liner directs a thin film of cooler bypass air along the inner surface. This creates a thermal barrier against the afterburner flame. Afterburners are often ignited by a hot streak. The engine momentarily overfuels the main combustor, sending a tongue of flame through the turbine to ignite the afterburner mixture. Modern engines use high-energy spark igniters, or torch igniters. These ensure the afterburner lights reliably, even at high altitudes where the air is thin and combustion is difficult. In turbofans, the afterburner mixes core exhaust with bypass air. This provides even more oxygen, allowing for massive thrust gains, though at the cost of complex mixing dynamics. Afterburners are critical for heavy carrier-based aircraft. They provide the necessary acceleration to reach flying speed within the short distance of a flight deck, despite the high fuel cost. The transonic region involves high wave drag. Afterburners provide the brute force necessary to push an airframe through Mach 1 and into the more efficient supersonic cruise regime. The Concorde used afterburners, or reheat, during takeoff and for the acceleration phase to Mach 2. Once cruising at supersonic speeds, the engines reverted to dry thrust for efficiency. The SR-71 used unique bleed bypass tubes that directed air from the compressor straight to the afterburner. At Mach 3, the afterburner acted more like a ramjet. Adding too much heat in a constant area duct can cause thermal choking, where the flow cannot accelerate further. Proper nozzle expansion is the only way to avoid this physical limit. At high flight speeds, the air entering the engine is already highly compressed by its own velocity. This ram effect increases the efficiency of the afterburning cycle significantly. Using an afterburner increases the infrared signature of an aircraft by several orders of magnitude. This makes the plane an easy target for heat-seeking missiles from miles away. Modern fifth-generation fighters aim for supercruise, which is supersonic flight without afterburners. This preserves fuel and maintains a lower thermal profile while still achieving high-speed mission objectives. Afterburners require massive centrifugal fuel pumps. These pumps must deliver hundreds of gallons per minute to maintain combustion in the high-speed, high-pressure environment of the augmented duct. The afterburner duct is made from heat-resistant superalloys like niobium or cobalt. These materials must maintain structural integrity while exposed to internal temperatures that would melt steel. Engineers model afterburners using Rayleigh flow equations, which describe heat addition to a compressible fluid in a constant area duct. This predicts how pressure and Mach number will change. Afterburning is a highly irreversible process that generates massive amounts of entropy. This fundamental thermodynamic inefficiency is why it is never used for primary long-distance propulsion. The hardware inside the duct, like flame holders, creates drag and total pressure loss even when the afterburner is off. This slightly reduces the dry thrust efficiency of the engine. The variable nozzle is usually driven by hydraulic actuators or fuel pressure. These must respond in milliseconds to changes in throttle position to prevent engine damage from pressure spikes. In short takeoff and vertical landing aircraft, augmented thrust can be used to provide the massive vertical force needed to lift the plane's weight without the benefit of wing lift. Because the residence time in the afterburner is so short, achieving 100% combustion efficiency is difficult. Unburnt fuel can sometimes be seen as dark smoke in older designs. Future research into plasma-assisted combustion aims to improve afterburner efficiency. Using electric fields to ionize the air can speed up chemical reactions and stabilize flames in thinner air. In addition to high-frequency screech, afterburners can suffer from low-frequency rumble. This is caused by bulk pressure oscillations in the duct and sounds like a deep, rhythmic thumping. The main advantage of afterburners is their excellent thrust-to-weight ratio. They provide a massive power increase for very little additional hardware weight compared to a larger dry engine. When exit pressure is lower than ambient pressure, the plume is overexpanded. The atmosphere crushes the exhaust inward, creating a series of shock waves to equalize the pressure. At high altitudes, the thin air cannot contain the high-pressure exhaust. The plume expands outward rapidly, creating a wide, fan-shaped trail that is characteristic of high-altitude flight. Moving the throttle from idle to full afterburner requires a complex sequence of valve openings and nozzle adjustments. Modern digital engine controllers manage these variables to ensure smooth transitions. Before entering the afterburner section, the gas must slow down to increase static pressure and improve combustion stability. A diffuser section converts kinetic energy into the required pressure rise. A significant portion of afterburner energy is lost to radiation. The white-hot gases emit intense electromagnetic energy that heats the surrounding air and engine components without contributing to thrust. Some afterburners have multiple zones or stages. This allows the pilot to select partial augmentation for cruising or full augmentation for combat, providing better control over fuel consumption. There is a diminishing return on adding heat. As velocity increases, the kinetic energy required scales with the square of speed, meaning each additional degree of temperature provides less thrust boost. Advanced flame holders use specific shapes to generate turbulent vortices. These vortices mix the fuel and air more thoroughly than a straight flow, allowing for a shorter and lighter tailpipe. Low bypass engines are better suited for afterburning because their exhaust is hotter and denser.
High bypass engines struggle with afterburning because the cool bypass air is harder to ignite.
At extremely high altitudes, the air becomes too thin to sustain an afterburner flame. This defines the functional ceiling for most interceptors, as they lose their primary speed advantage. The extreme thermal cycling of an afterburner shortens the lifespan of engine components. Every second of afterburner use is recorded and factored into the maintenance schedule for the aircraft. Modern nozzles can tilt the afterburning plume to provide maneuverability. This allows for post-stall maneuvers, where the pilot controls the aircraft's orientation using the engine's raw power. Future zero-emission concepts explore using hydrogen for afterburning. Hydrogen's high flame speed and energy density could make for more compact and powerful augmentation systems than kerosene. Beyond combat, afterburners serve as an emergency power reserve. If an engine fails during a critical flight phase, the remaining engine can use afterburner to maintain safe flight speeds. Ultimately, afterburners represent the thermodynamic brute force of aviation. They trade efficiency and stealth for the unparalleled ability to generate massive thrust on demand through rapid fuel combustion.